So if you look at chapter 8, right there at the beginning of the chapter, it starts out, with the topic of alternating current. And it starts out with the sine wave, like this. Very familiar curve. And I thought maybe what I would do is just develop that concept a little bit, because quite frankly, why not? Why is alternating current a sine wave? Why isn't it something like this? Why isn't it something like that? Or why isn't it a triangle wave? Or why isn't it a square wave? What's so special about a sine wave? And everything boils down to, in terms of the sine wave, everything boils down to how the power is generated at the utility. How are generators built? How are they designed? And I was just rooting around through some of the cabinets next door, and apparently in another class, they built these contraptions. Those are actually generators, little models. So this looks like an DC generator here. These little arms are called commutators. And I wish I had known these were over there, because I could have gotten them running and showed you some stuff. But basically, I'm going to just pick this one here. We're looking at actually I'm going to reverse that a little bit. But a typical generator has two components. You have a stator, which doesn't move. And you have a rotor, which does move. So this is the stator. And then you would have the rotor, which is this guy here, and of course that does move. All right, so that rotates. And so I'm showing a permanent magnet. I've reversed. You can show the permanent magnet here and have this center part have the windings, and then you transfer power to the outside world through these, they call them commutator bars or slip rings, depending upon whether it's AC or DC. I'm showing, so this has the permanent magnet as the stator. I'm showing the permanent magnet here. And so as a permanent magnet, you've got your magnetic field here, like so. And then that magnetic field sort of bends around like this. And on the sides of the magnet, it's not as strong. You cannot have a north pole without a south pole. It's impossible. So you can have a positive charge and a negative charge, but that doesn't work for magnetic field. So every line of force that I'm showing out of that north pole and comes back to the south pole somewhere, somehow. And so that's my rotor. This thing turns. How does it turn? Well, there would be a shaft connected to a steam turbine or a gas-fired contraption, and that would physically turn that rotor. And as the rotor spins, the magnetic field will cut across the windings of the stator. So these guys would be connected, and that's your output right here. And there's a law, it's not in your book, but there's a law called Ampere's law that says whenever you have a magnetic field intersecting or cutting across a conductor, you're going to generate a voltage. And so on the stator, when you get this thing spinning, you're going to see a voltage on these output terminals. On this guy here, so the permanent magnet is here, you got a north pole here, south pole here. If I were to just spin that, and then I would pick off the voltage off these little things which kind of slip, or they're kind of stationary with respect to the shaft. And that's how that would work. So what exactly is going to happen? What will you see at the output when you turn that? Well, when the rotor is offset by 90 degrees from the stator, you'd have something like this. And you have your magnetic field lines like this. And very little, if you just take a snapshot at that point, so you have very little interaction between the magnetic field and the conductors. And it's rotating, but we're going to stop it right there. And as this thing rotates, I'm going to say clockwise, the magnetic field, the more powerful portion of that magnetic field is right at the North Pole and right at the South Pole. And the North Pole is going to start, the magnetic field is going to start cutting through those windings more and more and more, much more intense. Same way with the South Pole, it's coming down this way. And what I'm doing is, now you could flip the windings, you could put these windings clockwise or counterclockwise, and the current or the voltage generated here would be opposite to what's going on here. But what I'm going to do is, I'm assuming that the voltage generated here reinforces the voltage generated here. So you have an overall net output. These windings plus these windings equal V out. And so if I were to plot the output, I would start out in this position with virtually nothing. And as my rotor rotated clockwise, the voltage would increase, like so. Gets top dead center, maximum voltage. All right, and now the rotor continues on through, and as it does, the output voltage begins to drop like so. So at this point here, I rotated 180 degrees. I'm now like that. And now my North Pole is going to be cutting through the windings at this side, on this side. And so the output is just going to reverse. It's going to be like that. And this position right here corresponds to this position. Okay? And you just keep going like that. So you have something like this. All right, that's pretty pathetic, but for a diagram. Now, what I drew is not really a sine wave, but it's sort of like a sine wave. I mean, the early generators, as soon as engineers realized that they could mimic a sine wave with a generator, they thought, well, hey, if we can modify the design of our generator so that we actually do produce a sine wave, we have a whole branch of mathematics already in place called trigonometry that we can analyze what's going on. All right, so that almost from day one, the design of generators started to change so that the output would actually be a sine wave. And what they did was they changed the stators, and this is the way generators are today. to make them flared. So the poles on a generator kind of look like this. And this guy is what looks like that. And then you have your rotor like so. And so the idea is when you put wings on this, on each one of the poles, the vertical transitions are not quite as vertical. It actually looks more and more and more like a sine wave. And in fact, with technology the way it is, generators produce almost perfect sine waves. So you know, you have something like this. I don't know if that's any better than the other. But that's the idea, okay? So that's the idea. And that, in a nutshell, is why you have alternating current represented as a sine wave and not a square wave and not a triangular wave or a step function or whatever. It's just a quite naturally, it's an offshoot of how power is generated. As a matter of fact, in the chapter they talk about polyphase power. I'm not really going to dwell on that, but you can see that right in here, there's a lot of empty space. Okay, right over here, there's a lot of empty space. And in fact, modern generators have 3 sets of poles. So they'll have a set here, and that matches up with a set here. And then you have a third set, like so. Now I'm drawing the permanent magnet on the stator for this example. So that rotor is, when that rotor turns in this kind of a generator, this is called a polyphase or 3-phase generator. It's always intersecting a magnetic field somewhere. So the output is not just this. The output is 3 sine waves superimposed one on top of the other. So you have a second set like so, and then you have a third set like so. Okay, so that's called a 3-phase polyphase generator. And then that leads to a whole new set of equations. We're not going to get into it, but it's just mentioned in your book, so I'll just draw it and show you what's going on. Okay? So once you have a sine wave, once you represent alternating current with a sine wave, the next step is to quantify it, to give it some definable characteristics. Oh, by the way, one thing I should note is that sometimes sine waves, you can represent this x-axis in 2 different ways. You can represent it in terms of time. So sometimes you'll see that just as seconds. Or you can represent it in terms of an angle. You can represent it in terms of a degree. Because remember, this thing is generated as a result of the generator spinning through 360 degrees. So every one of those positions, if you just stop it in time, every one of those angular positions corresponds to a point on the sine wave. So sometimes you'll see the x-axis expressed in terms of time, and sometimes you'll see it expressed in terms of an angle. Regardless, you've got a sine wave. So the first thing that we do is we want to quantify this, and the first parameter that is mentioned in the text is the peak value of the sine wave. So if this is a voltage, that would be, the peak value is the value of the wave from the x-axis to the topmost peak. Could be here, since these are symmetrical, this is also VP down here. So you just take one or the other. And then the second parameter that is mentioned is what is known as the instantaneous value. And that is nothing more than the value of the wave at any instant in either time or any instant in terms of angle. So that would be an instantaneous value. This is an instantaneous value. And there are an infinite number of instantaneous values. You just pick a point on the wave. And then the third parameter is what is known as peak to peak. And that's no mystery, right? Is it? It's just the value from here to here. So peak to peak value is twice the peak value. There are times, now you say, well, that's dumb. I mean, why even, if you know what the peak is, why even bother with the peak to peak? Well, the reason is that sometimes a sine wave, an alternating current wave, is superimposed on top of a direct current wave, on top of direct current rather. And so if what you're doing is offsetting the zero position either up or down. So you might have a sine wave like so, that's up here. It's offset. And it's not readily apparent in that situation, not readily apparent what the peak to peak is. You just have to look at it a little bit. So here would be your, this is known as a DC component or DC bias. So sometimes the peak to peak is useful. I don't get into it that much, but that's what it is. And then the fourth, there is an average value in the text, which I don't know that I've ever used it whatsoever. If you look at this, but it's in there, so if you look at this waveform, you say, if I said, well, what's the average value? Well, the average value is 0, because half the waveform is above the line, x-axis, the other half is below the x-axis. But in the book, what they do is they say, well, the average value is the average value of just the positive portion of the wave or just the negative portion of the wave. Okay? That's defined as the average. So the fifth parameter is what is called the root mean square value of the wave. If you look at this wave here, and you superimpose that alternating current wave onto a direct current waveform, you're going to have something that looks like this. So it has one is superimposed on top of the other one. And you can see just by looking at this that if you were powering, let's say if you're powering a light bulb with this waveform, direct current, and you were powering the same wattage light bulb with alternating current, intuitively you're going to see that the light bulb that's powered from the alternating current is not going to shine quite as brightly as the direct current, because there are places where, for example, right in here, the DC source is providing power, a constant power, throughout that whole cycle from here to here, but the alternating current is approaching a maximum value and only reaches a maximum value for an instant, and then starts to drop down. And if I take this negative portion of the waveform and just bring it up here, just for illustration purposes, this would represent the electrons going in another direction. So here the electrons are going one way, down here they're going another way, but they're still providing power to that light bulb. But if you compare the two curves, you're going to see that here as well, the light bulb that is being provided power from the direct current it's that DC source is providing all that energy, and here in the AC source you got that big gap. Same way over here. So one light bulb is going to shine brighter than the other one, and even though they both have the same peak value. So the question is this: at what peak value do I have to increase my AC source so that the power delivered to that light bulb is the same as the DC source? How much do I have to increase the alternating current waveform so that those two loads have this delivered to them the same amount of power? So it would be, I'd have to increase that AC wave somewhere up in here, make it look like that. And if I did that, then the gap that appears here, the deficiency that appears here, would be made up for in the excess up in here, okay? So those two would be equal. And the RMS value, the root mean square value of an alternating current wave, is that value of alternating current which produces the same power as a DC source. Okay, and here's how it's calculated. It's not easy. It's not too bad, but it's a little bit cumbersome. So the formula for the root mean square voltage is this. Take the square root of that. And what are those V1s, V2s, V3s, V4s, all that good stuff? V1 is just a point on the waveform. If V1 might be here. If I were to divide this waveform into equal parts, V1 would be here. So it would be this value. V2 is this value. V3 is that value, all right? So what I'm doing is just picking points on my wave. It doesn't have to be equally spaced. It can be staggered. And the more points that I analyze, the better my answer is going to be to the actual VRMS value, okay? So if I have if I'm looking at 10 points, the actual value where the AC wave is equal to the DC wave is going to be very, very accurate. If I pick 20 points, even more so. Obviously, if I have an infinite number of points, that's when it's going to be exact, and that's where calculus comes in. If you want to find the RMS value based on an infinite number of points, then you have to use calculus to do that. But we can get very, very, very close with just a discrete number of points, 10, 15, whatever. Okay? But that's the formula. So the question is, what is the RMS value for so we're at, when you take a reading of an AC outlet, a receptacle outlet, you get what, 120 volts? And that is always RMS. What you're reading is root mean square. But the peak value for an RMS voltage of 120 volts is somewhere around 170 volts. So the peak, and I want to have you do a little exercise, but the peak value is typically, it's equal to the square root of 2 times V RMS. So that's the relationship, where the square root of 2 is 1.41414. Square root of 2 is 1.414. So that comes to 169.7 volts. So if you were to put an oscilloscope, stick the probe into a receptacle and actually look at the waveform, the peak value for a standard receptacle is going to be about 170 volts. Even though that receptacle, your meters will show 120, 115, 110, just depends on where you are. Okay? That's the formula. And that's exact. So let's go through a lab, little exercise, where I'd like to have you calculate the root mean square, because VRMS from now on, now to the end of the course, when we're talking about alternating current, it's going to be root mean square, RMS. We're not going to be dealing with peak or peak to peak or average or any of that stuff. It's all RMS. That's the industry standard. And here's what I'm going to have you do is calculate the RMS value for a sine wave. And so what you're going to be doing is for a particular degree, the chart that I'm going to have you fill out shows this. I want you to calculate the sine wave using on your calculator for a variety of degrees. So it would be 15 degrees, 30 degrees, 35 degrees, whatever. So let's just say, Russell.
Sorry, the V is the equation for VRMS over the whole number?
Yeah.
Over number, right?
Yeah, the whole thing. So that n is inside of the
That's all.
square root.
Thank you.
So if you have, let's say you have 15 degrees for this starting point here, that would be 15 degrees might be this point right there. And I'm assuming that the x-axis is in degrees. The sine of 15 degrees is 0.2588. So that's your first point. Then you're going to square that, and you get 0.0698. And then that's the number that you put in here, 0.0698, okay? Second angle, 30 degrees. Third angle, 45 degrees, and so on and so forth. Get those squares, you add them all together, divide by the number of points that you're taking, and 0, I'm going to have you find the first angle is, well, the first angle is 15. Sometimes I choose the first angle to be 0, that counts as a point. So you divide by n, take the square root of that whole mess, and that gives you the root mean square of a sine wave, okay? I kind of gave you the answer, but I'd like you to go through the calculation anyway, because this is important. So there's that. Where's everybody tonight?
I don't know. All the good weather.
Was there like a...
It's a good looking day today too.
There are actually some students missing today in my classes.
Really?
the song, yeah. They must have been like, forget this school day, we're going out.
Every single week. Because then something you're doing it just happens to us.
I don't know, Russell, I mean, this is 1/3 of test number 3. I mean, it's,
This is the make it or break it.
That's right.
Make sure you have the others. Because you plan to do yours right now. I guess. Oh, good. These are well-made ones. When is TJ on the same? I'm just mad he destroyed me. I'm telling my grandchildren about this. He's one of my biggest supporters.
Good. Say 15. So here it is. That would be right.
Yeah, that would be the point on the wave. So this would be, so for that particular angle, this is the value of the sine for that particular angle. You would just take 15 degrees and then push sine.
That's sine, cosine.
Yeah, okay, yeah.
Still got something.
And 0.25 what do you get?
Like 6.928.
Just
Sine
look at
15.
0.6598? 106. Is your calculator set for radians or degrees?
Oh, you know what? Because it is 15. There we go.
Okay, you got it? And then you square those numbers.
We got different answers. One of us is wrong.
You both could be wrong.
That's it.
Yeah, I think we're-
At least one of us is right.
What are you getting? Or just one? 125, what are you getting?
Not right.
What is this your calculator? Do you have it set for radians or degrees?
Should be in degrees.
Degrees.
Okay, so, I mean, it was in degrees, but.
125. Well, you got the same
Well,
answer.
for now, or when you put it in the solution.
Yeah. Okay.
Was I supposed to multiply by 170? Or,
I mean, yeah, to get the peak value is 170. So this is correct, it's 0.707. And then, so this gives you the voltage of the standard receptacle, which is 120.
okay, so
So there's something,
Yeah,
you're not adding.
I have these values, right?
Yeah,
Okay.
and did you divide all those values by 2? 1, 2, 3, 4, 5, 6, 7, by 12.
Okay.
Yeah, and then you take the square root.
I figured out it equals the square root of 2 over 2.
It does, yeah. Did you get it? Did you get it or still on?
I got 0.7.
Oh, that's close.
Close enough.
What are you getting?
0.771.
Yeah, that's good.
That's a big sine.
You're getting
0.07.
What is it?
0.07. That's what I do.
0.07.
Yeah, I'm not sure.
This is like analog logic.
Honestly, I forgot sign even existed.
You forgot to sign even.
Since I've actually done anything like this.
Well, you're off by 10.
I forgot that whole thing.
Is that in
It's just a
degrees?
regular,
Degrees?
no, it's just a
You
regular.
really got that correctly.
Okay, so this is correct, 0.25. So if you have 15 degrees and you take the sine, you get 0.2588. Okay, you got 2.2581. Now you square that, and you get 0.06 sine, or
Okay.
0.0698. So you got 3.87. How'd you get that?
Maybe it's. You see?
Here, I have an extra calculator.
That's what I need to get.
This is reverse
So
Polish.
6.06.
So it would be 15 degrees, so it's the sine of 15 is equal to 0.258. And then you have to take the square of that?
Choice, right?
No.
You can just go back.
So answer. Let's start over. So sine of 15. Enter. Square root of that, that's it. 0.0669. You can use this. Yeah. So you just keep doing that all the way down. So here's the, so So you forgot trigonometry.
Yes. Haven't done anything with trigonometry
Well-
since 2006.
You know, in electrical engineering, of course, we're generating a sine wave based on what is happening physically. So that rotor's turning, and when it hits 15 degrees from top dead center, it's producing an output voltage that is like 15 degrees on the sine wave away from the zero axis. Okay, so you're generating this sine wave. So the physical location of that rotor corresponds to where you are on your equation, on your waveform. But in mathematics, they don't talk about generators. The sine is, it relates to a triangle, and if this is the angle you're talking about, it's the ratio of this side here to the hypotenuse there. So the sine theta is equal to y over h, and that's it. It's just the ratio of those two sides, and they could care less about generators, right? So you're going from the physical to the abstract, but when you work out this equation, you still get, and as this angle changes, and that ratio changes, and you get these numbers, that it's the same numbers. That's all the sine is. It's the rate. Trigonometry is nothing more than the mathematics of triangles. So in this case, if that's the angle, could be this angle. If you're looking at that angle, alpha, the sine then is the relation, and this is x, sine of alpha. Another angle is x over the hypotenuse. Okay, then it's that way. But it's still going to give you the same result as this angle changes. It's just a matter of how you visualize it. There's nothing magical about which angle you pick. So, and that's why I said early on that when engineers realized almost from day one that they were generating a waveform that was very close to the sine wave. They just modified the design of the generator so that it would produce a sine wave. And then now you have a whole branch of mathematics that you can use to analyze your system. So that's it. We're not going to be spending a whole lot in terms of the trig. But I just want you to get a good visual of what's going on there. So. So what did you get? So everybody get 0.707? Russell, you're still working a little bit, but you'll get it. Yeah. So it's, if you have a voltage of 170, and you take 0.707 times that, you get 120.19 volts. So the voltage when the peak is when the peak is 170, the RMS is about 120. And that corresponds to a standard duplex receptacle. So you get, when you get shocked, if you've ever been shocked and sticking your finger in a receptacle or working on something when you thought it was dead and it isn't dead, and I've been shocked more often than I care to admit. You're exposing yourself not to 120 volts, you're exposing yourself to 170 volts. And it's a little bit of a kick, okay? A little bit of a kick. Now there's one thing I want you to see, and that is, there's one characteristic I didn't talk about, and that is the frequency and and the reciprocal of the frequency for a sine wave, which is called the period. The frequency is just the number of cycles that a sine wave completes in 1 second. So if we have an x-axis that's measured in seconds, in this case, and we've got 1 second here, and this guy's doing this. So we have 1 cycle, 2, 3, 4, 5, 6, 6.5. So that frequency would be 6.5 cycles per second. I want to make it even, I'll put one right here. So there's 6 cycles per second. Okay, and then the frequency, the designation for the frequency is F, and it's measured in hertz. Although I know just as many people who say cycles per second, but if you were talking about that sine wave, it would be 6 hertz. HZ, which stands for this. Who was an early engineer in the early 1900s, that's named after him. And if you take the inverse of this, so let's just say frequency is equal to 6 hertz or 6 cycles per second. I like cycles per second because it introduces the concept of time. If you take the inverse of that, that would give you the period, or for that particular sine wave, the period would be 1/6 of a second per cycle. How long does it take for 1 cycle? For that amount of time is 1/6 seconds per cycle. So the frequency is just 1 over the period. And the period is designated by the letter T. Okay?
You said it was called the period or the what?
Period.
Or what is the T just stands for period?
T stands for the period.
Okay.
It would be the cycles per second. Frequency is, I got that backwards. Period is seconds per cycle, and frequency is cycles per second, or hertz. And when you're doing calculations, remember we talked about dimensional analysis, where you write down the dimension and you cancel out the numerator and the denominator. If you're ever doing a dimensional analysis with frequency, you never really count cycles. You never even write that down. You just, frequency is 6 something per second, and then period is seconds per cycle. You don't even worry about the cycle part of it. It's not a dimensional number. Okay, anybody have any questions? RMS. So when we're talking about generating a sine wave electrically with a generator, you can see that the faster this guy rotates, the faster that rotor spins, the higher the frequency. Okay? And so there's a relationship between rotational motion and frequency in our situation. And in the world that we live in, I don't know about you, but the measurement of angles that I'm most familiar with and that I'm most comfortable with is degrees. I mean, it's my son is a snowboarder, and he's a very good snowboarder, and when he's, you know, on the slopes and he goes into a half pipe and he comes out, he always talks about doing a 360 and a 540. I mean, what he's talking about is degrees, okay? Or an ice skater jumping up in the air and spinning.